Welcome to Fantastic Vision. Please subscribe us before you watch today's video. In the current mainstream technology route, deep ultraviolet lithography and extreme ultraviolet lithography constitute the dual pillars of the industry. DUV lithography uses a 193 nanometers wavelength light source, combined with immersion technology and multiple exposure processes, to achieve a 7 nanometers process node, but it needs to rely on complex processes to compensate for the distortion of graphics caused by diffraction effects. In contrast, EUV lithography breaks through the resolution limit with a 13.5 nanometers wavelength light source, and a single exposure can support processes below 5 nanometers, significantly reducing process complexity. In 2020, the penetration rate of EUV lithography in global chip manufacturing reached 13%, and it is expected to increase to 31% in 2024, becoming the core support for advanced processes. Obviously, the scale-up of EUV technology faces multiple physical and engineering challenges. First, the high numerical aperture, high NA, upgrade requires the numerical aperture to be increased from 0.33 to 0.55, which requires the mirror flatness tolerance to be controlled within 0.1 nanometers, equivalent to 1/5 of the diameter of a silicon atom, and the manufacturing cost soars, with a single device selling for more than $150 million. Secondly, the generation efficiency of 13.5 nanometers light source restricts production capacity. The energy conversion rate of tin droplet laser plasma solution is only 0.8% to 1.2%, and it needs to be matched with 250W light source to meet mass production needs. The current commercial light source power limit is 200W, and the wafer throughput is limited to less than 170 pieces per hour. In addition, the mask defect rate directly affects the yield rate. The defect density of EUV reflective mask needs to be less than 0.001 square centimeter, but in actual production, due to multilayer film stacking process errors, the defect rate is still as high as 0.03 square centimeter, resulting in a 28% increase in chip mass production costs. Faced with the approach of physical limits, the industry technology route presents a multidimensional breakthrough trend. In the field of materials, dry photoresist technology replaces the traditional spin coating process through vapor deposition, reducing the line edge roughness, LER, from 3.2 nanometers to 1.5 nanometers, improving the fidelity of 3 nanometers node graphics. At the equipment architecture level, the multi-beam direct writing system uses 512 electron beams to scan in parallel, increasing the writing speed to 10 mm² RS, providing an alternative path for processes below 1 nanometer. It is worth noting that advanced packaging technology is partially replacing the single-chip miniaturization path. TSMC's CoWoS, chip-on-wafer-on-substrate, solution integrates 4-5 nanometers chips through a silicon interposer, which improves performance by 40% and reduces costs by 60% compared to monolithic designs. In 2024, this technology will drive the global advanced packaging market to $7.8 billion. Accelerated reconstruction due to technical barriers and supply chain risks. Domestic DUV lithography machines have achieved mass production of 28 nanometers processes, and combined with double exposure technology, they can cover 14 nanometers nodes, with a wafer yield of 92%. In the field of core subsystems, Shanghai Microelectronics Light Source Collection Module adopts a molybdenum silicon multilayer film anti-pollution design, and the lens life is extended to 9,000 hours, 50% higher than the international standard. The immersion control system developed by Zhejiang University achieves a liquid film thickness fluctuation of plus or minus 0.05 micrometers, meeting the stable operation requirements of immersion lithography machines. Disruptive technology exploration is promoted simultaneously. The accuracy of proton beam lithography of the Chinese Academy of Sciences reaches 2 nanometers, which is suitable for military radiation-resistant chips. Tsinghua University's multi-electron beam system achieves 50 beams of parallel etching, with a throughput of 5 pieces per hour, laying the foundation for carbon-based chip manufacturing. ASML occupies 91% of the global high-end market share with its EUV monopoly, but its supply chain relies on German Zeiss objective lenses and Japanese vacuum chambers, and geopolitics has extended the delivery cycle of key components to 18 months. In the first quarter of 2025, ASML's revenue share in China dropped from 42% to 18%, and its market value evaporated by 32 billion euros, reflecting the impact of export controls on the business ecosystem. In contrast, the third phase of the National Integrated Circuit Industry Investment Fund invested 450 billion yuan in China's semiconductor industry, of which lithography machine special projects accounted for 23%. And supporting materials such as Nanjing University Optoelectronics photoresist had a purity of 99.999999999%, meeting the requirements of the 7 nanometers process, and the localization rate increased from 2.5% to 19%. ASML China president warns that continued blockade will shorten the commercialization time of China's EUV lithography machine to 5 to 8 years. The paradigm shift of lithography technology has surpassed the logic of simple process miniaturization. The cost dimension shows that the cost of a high-NA EUV unit is $180 million, while the cost of China's free electron laser (FEL) solution is controlled at 280 million yuan, and energy consumption is reduced by 80%. In terms of material innovation, the thermal expansion coefficient of silicon carbide lenses, 0.8 times 10 Ak, is 90% lower than that of fused quartz, 0.5 times 10 Ak, and the thermal stability is significantly improved, supporting higher power light source operation. According to the International Roadmap for Equipment and Systems, IRDS, the 1.5 nanometers node in 2030 will rely on the collaboration of ultraviolet light sources and self-assembly lithography technology, marking the official entry of lithography technology into the era of atomic-level control.